So, Mythbusters has this crazy idea that if you shoot a gun horizontally, which is just parallel to the ground is flat, and it's a surface that's, yeah, let's just leave it at that. If you shoot a gun that's horizontal and you drop a bullet from the same height as a barrel, they will land at the ground at the same time. So if you fire the bullet and at the same instant you drop the bullet, another bullet, they will hit the ground at the same time. Let's see if it works.
2, 1. But from 360 feet away, the boys can't see exactly where the fire.
Of course he rides a unicycle.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. Ugh. I can't wait to see the high speed. So, dude, this bullet carved a streak right under the drop zone. I think this might be the shot we've been looking for.
In real time, it's impossible to tell what happened. Until Adam analyzes the high speed and crunches the numbers.
Okay, so it's right afterwards. They get a few milliseconds off, and from what I can see in this whole setup here, this is just due to error involved in perhaps dropping the bullet or perhaps shooting the bullet. It's not exactly the same. It should be exactly the same, which is really weird. This is a fact that just when I first was learning physics, I can remember back when I was first learning physics, the very first time, I could not accept this. How could something that's just thrown sideways and another object that's just dropped hit the ground at the same time? It doesn't make sense to me. But it's how the world works. It's true. It's so weird. You can try this for yourself if you want to. Let's just say you have like a table and some object to push off the table, and you drop another object at the same height at the same time as you push the other object off the table. They will both hit the ground at exactly the same time. It happens. It's real. And it's weird. Here's a picture of an object that was thrown sideways slightly, and then another object, and the same object just dropped. And it was photographed using strobe lights. And just they left the camera on for a long exposure, and they just got all the images of the ball, looks like, being dropped and the ball being slightly hit off to the side. And you can see every instant along here, every strobe, the balls were falling at exactly the same rate. It's just this one had some horizontal velocity involved with it. And that's what's so weird. The vertical component of this motion is completely independent of the horizontal motion of this vertical. It's so weird. The horizontal can just do whatever it wants. It could be going really fast. It could be accelerating away, but it's still going to drop at the same rate. It's so strange to me. But it's cool because now we can answer some interesting questions about how far this object is from where it would have just dropped and hit the ground. And the way we do that is through this variable of time, the time it takes for an object to hit the ground. And you're going to see how this works in these problems, especially this warm-up problem and, the practice problems that we do as well. So let's get this warm-up problem started. Let me erase this by putting another one on here. Okay, here it is. Don't save. There it is. There he is. He's a naughty little boy, and he's thrown horizontally off a cliff. This is a warm-up problem in your packet. And the cliff is 78.4 meters high, and he's thrown off at 5 meters per second. So if you have a cliff like this, let's just say it's a cliff like this, and there's the ground. And this boy And he's naughty, so it's okay to throw him off the cliff. Look at him. He is so naughty. He's got that look about him. You could just want to throw him off the cliff. He's thrown off a cliff. There he goes. Wow! He's thrown off the cliff, and he's got a horizontal velocity of 5 meters per second. Okay, let's write all the things we know about the scenario so far. So we know that the cliff is 78.4 meters high. So this whole cliff is 78.4 meters high. We know that he's thrown off at 5 meters per second. Is there anything else we know in this situation? We do know gravity. Gravity equals, we now know it's 9.81 meters per second squared. Right. So he's thrown in this way. He's gonna take this path that looks something like this. We've seen this path before whenever we drop something. It looks kind of like this. Splat. Oh, we don't have to make him splat. We can have him hit a pillow if we want to. I don't know. So he's thrown off a cliff, and he's got this horizontal velocity. He's got a vertical motion as well. Now, the vertical motion turns out to be just the same as if he'd be dropping straight down. So we can solve for that problem. We could solve for, let's say, like how long it takes for him to get down. We could solve for how fast he is at the very bottom if we wanted to. All those things we can solve. And this distance this way is all determined by the amount of time that he's going 5 meters per second. So, in other words, this distance from here to here is his displacement. So that's his delta S. 78.4. And we have an equation. I believe we have an equation that can solve for this. If we're given delta S, if we're given the acceleration, and if we're given, let's say, like an initial velocity. His initial velocity, oh, I forgot to write that. His initial velocity in the vertical domain is 0. Because he's basically just being dropped vertically. He's not being pushed down. He's just being thrown horizontally that way. So vertically speaking, that motion has nothing to do with him. Okay. Make sure that makes sense to you before you keep on going. The vertical motion is independent of that horizontal motion. So we can use this equation that we've used lots of times before, which is delta S equals 1/2 a delta t squared plus u delta t. All right. We know what delta S is. We know what a is. It's actually the same thing as g. It's acceleration going downwards. We don't know what t is. And we want to find out what t is because that's what this is saying here. How long does it take? So that's asking for delta t. We want to know what delta t is. So we can solve for delta t. This right here, this whole term right here, since u is 0, this whole term is going to turn into 0, which is kind of convenient for us. So now if we want to solve for delta t, let's just rearrange this equation a bit. So it's going to be, we're going to first multiply both sides by 2 to get rid of this 1/2 on this side. So it's going to be 2 delta s equals a delta t squared. Now we divide both sides by a, so it's going to be 2 delta s divided by a equals t squared, delta t squared. So now to get delta t by itself, you want to square root this. So it's going to be square root of 2 delta s over a equals delta t. Now all we have to do is plug in these values. So let's do it. Ready? Now this displacement is a negative displacement. He's 0 here and he's going negative distance, or he's going in a negative position here. We could say that, or we could also say that he's accelerating positively in this direction. It's whatever way you really want to frame this problem. It's the lucky thing about physics is you can kind of define things how you like in order to fit this problem. Make sure it's physically represented correctly. So let's just say it's a negative displacement. So if it's a negative displacement, then we're going to have 2 delta s. Delta s is going to be negative 2 times negative 78.4 meters divided by, and now A is going to be actually this value right here, which is negative 9.81 meters per second squared, and we're going to square root the entire thing. And if you do all of that, you're going to get the value. You're going to get a value of delta t. So what is that? Let's put it into our calculator. Oopsies. Bring the calculator up here. I'm going to minimize this. And I'm going to minimize this. Put this up here. I need to have both at the same time. Come on. Oh, this is not going to work. Okay. I don't know why this didn't work. Why this worked before. Okay, so I'm just going to do this on my own calculator. Here we go. And you can do this as well. 2 divided by 9. And then the square root of that is going to be 3.99796. 3.99796. We only have 3 sig figs here, so I'm going to round it to 3 sig figs down below. So 3.99 turns into 4.00 seconds. Fantastic. How far from the base of the cliff does a boy hit the ground? Now this problem, we're going to do this fairly quickly. Since we know what our delta t is,